Hey guys, we're going to be continuing Chapter 7 here with Section 7, talking about exponential growth and decay. This is related to our last lesson. As you can see right here, we have a graph of an exponential function. So that's what we're going to be talking about. Make sure you pause and copy this down. Exponential growth is modeled by the function y equals a times b to the x, where a is greater than 0 and b is greater than 1. The base b is the growth factor, which equals 1 plus the percent rate of change is expressed. So you want to make sure you have all of this copied down because this will tell you how to do this. Today is mostly going to be evaluating, or kind of like a plug and chug. It's also a cool lesson because it's applicable to your everyday life, and you'll see that come up here in a little bit. But first, just gonna let you marinate in that one for a minute. All right, moving on. Okay, modeling exponential growth. Let's look at the first question. It says, since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. So we're going to be using the y equals a times b to the x, using that information from the other one. So y is going to be what I'm looking for. I'm trying to solve for that. The trend continues. How much will be spent at the restaurants in 2015? And then the next part is my initial amount. So 360 billion is what was initially spent. B is 1 plus my percent. So here it's 7% plus 1 is 1.07. And then x is the amount of time that went by, which in this case, it was 2005 to 2015 is 10 years. All right, so that's all I'm doing on this is substituting these values in, and then I'm solving for it. So I get, let's see, 360 times 1.07 raised to the 10th power, and you can just put all of this in your calculator. So you end up getting about 708 billion. Okay, so that's how much money was spent in 2015. Now take a look at this. It says, what is an expression that represents the equivalent monthly increase of spending at U.S. restaurants in 2005? So I'm going to take this initial part and fill some things in. So I get y equals, and then I'm going to be looking at this. Actually, let's get rid of the y equals. I'm looking at this part right here. The x I don't know, so I have 1.07. And to figure out monthly, whatever the number is of years, I'm going to multiply that by 12. So 12 times x is the number of months that I will get for x number of years. And then to find it per month, I need to divide by 12. So to find per month, I divide by 12. It's 12 times the number of months. So then this is using some of that stuff that we've been working on. This is weird looking. This is where you want to just copy the example down so that you have it, and then you'll basically just follow it exactly as I do it, because otherwise it could be really, really confusing. So here I have 1.07 to the 1/12, which is roughly 1.0057 to the 12x, and 12x just tells me the number of months, so it's going to be 1.0057. Instead of 12x, I'll change that to m for months. All right, so there are my two answers for these questions. Again, this one's weird. What you're going to do is take the number that is here and multiply it by x, and then divide that by 12. Okay, so we divide that by 12. Let's go on, and here's one for you to try. Go ahead and pause. The answer will be up in 3, 2, 1. All right, here are the two answers that I got. So hopefully you got the same thing. If not, go back and check your work. All right, compound interest. When a bank pays interest on both principal and interest already earned, that's called compound interest. This is your friend. If you're making an investment and you could get compound interest, that's good. If you're paying loans, it's not. Make sure that you copy all of this down. This is just a matter of chug and plug. You will have this available to you on your checkpoint from your notes, but I'll also give you the formula for tests too. So you do want to get some practice using it. So let's get some practice. So suppose that When your friend was born, your friend's parents deposited $2,000 in an account, paying 4.5% interest compounded quarterly. What will the account balance be after years? So we're just going to go in and fill in information that we have. The account balance is what I'm looking for. Equals the principal, which is $2,000, times 1 plus the interest rate as a decimal, so that's 0.045. And that whole thing is going to be, oh wait, I did minor mistake. Let me fix this real quick. Forgot the quarterly part. All right, so 0.045 is my interest rate divided by n, which is the number of times interest is compounded quarterly here. So that's going to be a 4. And then that whole thing is raised to the 4 times how many years, which in this case is going to be 18. All right, so it's a big ugly problem. It's not too bad. You could use your calculator for it. So I end up getting 2,000 times 1.01125 raised to the 72nd. And again, I'll just put that into my calculator again. And I get about $4,475.53, round it to the 3, okay, cents after 18 years. Now I want you to think about that for a second. 18 years, $2,000 more than doubled. No work was done. This is money earning money without you doing anything for it. So compound interest is certainly something that is a good thing that you want to be aware of. This is just a matter of substituting this information into the right places in the problem. So here's one for you to try. Go ahead and pause. The answer will be up in 3, 2, 1. All right, so here's what I got, $11,809.62. And that's just substituting this information. Be careful, this one was compounded monthly, so you want to use 12s on that. All right, exponential decay can be modeled by the function. This is where a is less than 1, or b is less than 1. Okay, so we're going down. You can see this is going to be a negative kind of function here. But it's still using the same thing. The only difference here is that this number is going to be smaller than 1, but greater than 0. Before it was 1 plus something. Here it's going to be minus something because it's decay. So a decay factor is 1 minus the percent rate. So let's see how this plays out. It says the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter increase in altitude, the pressure decreases about 11.5%. What approximate pressure at an altitude? What is the approximate pressure at an altitude 3,000 meters? So I'm going to go ahead and plug this information in. So my initial amount at sea level is 101. And then to find this next value, it's going to be 1 minus 11.5%. Okay, so that's going to be 1 minus 0.115, which is equal to 0.885. And then that whole thing is going to be raised to x, the amount of time, or in this case, it's not time, it's how it's changing. This says for every 1,000 meters, if it goes 3,000 meters, then that's going to be 3,000 divided by 1,000 is 3. Okay, so there's my decay, or my altitude in thousands of meters, right? So that x is the decay factor here. So let's go ahead and multiply that out. You could use a calculator. You end up getting roughly 70. Okay, so the approximate pressure is about 70 kilopascals. And again, it's just substituting in for that formula. All right, so here's one for you to try. The answer will be up in 3, 2, 1. All right, so here's the population that I got with everything substituted in there. Check your own work, make sure it's the same. And let's keep moving here. That's it. All right, so kind of a short video. Hopefully you took good notes. I'll see you all in class.